we're focusing on esters today. And so one of the characteristic things about esters is that they typically, not, it's hard to say absolutely, but they typically are pleasant smelling liquids, okay, used in perfumes and to make things smell better in general, any sort of commercial product. But also they are present in fats and vegetable oils. So you can see some examples here. So, imagine the smell of pineapple. Okay, that is methylbutanoate. Imagine the smell of bananas. That's isopentyl acetate. Okay, and any sort of fat has this, has this sort of structure where it's a triester. So how do we prepare esters? And again, a lot of this is repeat information. We've mentioned this before, but if you start with a carboxylic acid, there's a few ways to do it. One of them is more powerful, and that is through the conversion of the carboxylic acid into an acid chloride with the thionochloride. And then you can react it with pretty much any alcohol you want in the presence of a base, and you'll get an ester. But we have talked about another method that's used a lot called Fischer esterification, and that's here in the middle, where you acid catalyze a reaction between a carboxylic acid and an alcohol. And because that acid activates that carbonyl, it will work to make an ester, but that's typically used for making esters with pretty simple alcohols like ethanol, propanol, methanol, things like that. If your alcohol gets a little bit more complicated, for lack of a better term, then the best thing to do is to go ahead and make the acid chloride rather than attempting the Fischer esterification. Okay. Well, then the other thing that you can do is if you just react it with an alkyl halide and a strong base, the strong base would deprotonate the carboxylic acid, then the acid, or pardon me, not acid halide, the alkyl halide would then just form the ester, but that's pretty limited. But what goes on there, if you remember, is an SN2 reaction between the carboxylate, that deprotonated carboxylic acid, that's your nucleophile, and that attacks through an SN2 mechanism your primary alkyl halide to get an ester. But again, that's pretty limited in scope. But those are the three different ways that you can make an ester. Okay, so one unique type of ester that we talk about, I think I even introduced this in Organic 1, we're just going to kind of reintroduce it today. If it's a cyclic ester, and that has a special name, it's called a lactones. Okay, here's some examples of that where you can see you've got the carbonyl next to an oxygen, which is connected to a carbon group, but then that just loops around and becomes part of the carbonyl. Okay, so it forms a ring. And a lot of times, as you can see in this particular graphic that I put in here, that, and this isn't the IUPAC method, but you can talk about what type of lactone it is based on how far away the oxygen is. And so, like, for example, this is gamma butyl butyrolactone. Okay, so that means that the carbon that's attached to the oxygen part of the ester is at the gamma position. And now that we've had our discussion on mass spec, or I know that Dr. Donaldson introduces this earlier, you had him for Organic 1, you were using that designation technique of the carbon that's next to the carbonyl functional group. So there's your functional group, and the carbon next to that, that's the alpha position, and then next to that is the beta position, then the gamma, and then the delta. Okay, so you will see that terminology in naming, particularly with the lactones. Okay. All right, so let's talk about reactions of esters now. What kind of reactions do esters undergo? Well, we just talked about how to make them from a carboxylic acid, so it makes sense that you can revert it back to the carboxylic acid, and that type of reaction is called hydrolysis. Okay. Now, you can do this with an acid or a base, so in acidic conditions or basic conditions. And what you get, as we said in the heading there, you get the carboxylic acid back, and then the byproduct would be an alcohol. So as this shows you, you can do it. You can even do it in neutral water. It's just going to take you forever. The kinetics of that it's a really slow reaction, but you can catalyze it with an acid or a base. We're going to focus on the one that's catalyzed by a base. As a matter of fact, it's given a special name. It's called saponification. And so that's where you break the ester apart to produce the carboxylic acid and the alcohol under basic conditions. Okay, and here's the mechanism. So again, we start with our ester, and then the hydroxide ion, which of course is the ion that's present when you have a basic solution. It's your nucleophile, and it attacks the carbonyl carbon. So the pi electrons in the carbonyl bond move up onto the oxygen to give the oxygen a negative charge. And now you've got this tetrahedral intermediate, okay? So this is key. So, and this is a reversible reaction because right now we've got two potential leaving groups, really. We've got the part of the ester it's going to form the alcohol, so that green, what's color-coded in green there, or we have the hydroxide ion that I just attached. So that's why we say it's kind of a reversible reaction. But if that alkoxide leaves, if that RO group is your leaving group, then it gets us to a point where it's irreversible. And that's why ultimately this reaction occurs. Because now what you created is you created this RO with a negative, this alkoxide ion down here, okay? So it's going to undergo the most favorable, the most likely reaction that it can. And so that's going to be an acid-base reaction where this acts as a base and takes that acidic hydrogen. So my point being is that the reason why this reaction goes at all anyway is because this will not act like a nucleophile on the carbonyl. This alkoxide will act as a relatively strong base to take this relatively acidic hydrogen and just form the alcohol and move on, okay? So instead of this attacking the carbonyl, the easiest reaction is for this alkoxide to just grab that hydrogen and it just moves the reaction along. Okay, so you can see the next step is just that, where the alkoxide takes that acidic hydrogen from the carboxylic acid to create the carboxylate. And then typically what's done, if you really need to get the carboxylic acid, is in a second step, you just add some acid, strong acid, and it protonates that to become the carboxylic acid. But if you leave it as this ion, this carboxylate ion, and there's like a counter ion, let's say that it's like a sodium ion, because maybe this was NaOH to begin with, so you got the sodium ion out there. And so that right there is also known as soap, right? So this is part of the reason why this is an important reaction is because human beings have been doing this for a really long time. They take fat, which is, as I mentioned in the first slide there, is a triester, and they heat it up with lye, which has a lot of sodium hydroxide in it, okay? And you create these compounds where you got the carboxylate, and then it's got the counter ion there with the sodium, and that's used as soap, okay? So this is the process by which soap was made, and still is made. Okay, so that's the mechanism of saponification, which I do want you to be able to answer questions about. Okay, so now let's talk about a different reaction that you can do with an ester, and that is you can convert it into an amide. So remember that esters are almost at the bottom of that reactivity scale, but there's one functional group that's more stable than an ester, and that is an amide. So the consequence of that is that you can react an ester with an amine, and you'll get a reaction, and the product is going to be an amide. We call that aminolysis. So conversion of esters into amides, aminolysis. Now, remember that it will work, but it only works if the amine has at least one hydrogen on it. You can't do this with a tertiary amine. So, but not a tertiary amine. It will work with ammonia, or a primary amine, or a secondary amine. And so this just gives you all three potential examples. So you have your ester, you react it with an ammonia, and you just get what we call a primary amide. Okay, so that the whole designation of primary, secondary, and tertiary amide, pay close attention to that because, I just said in the previous bullet here, you can't do this reaction with a tertiary amine, but when you react it with a secondary amine, what you get is a tertiary amide. So, pay close attention to what we're applying that word tertiary to, okay? Because you can form a tertiary amide, and that just means that the nitrogen in the amide, this nitrogen right here, it's got three substituents on it. No hydrogens. It's got three substituents on it. Just that one of those substituents is an acyl group. Okay, but we can convert the ester into an amide with ammonia, or with a primary amine, or with a secondary amine. But if you start with a tertiary amine, you won't get a reaction. Okay. So another reaction that again we've seen over and over and over again is we can just take the carbonyl group and reduce it with a reducing agent like lithium aluminum hydride, and reduce it down to an alcohol. In this case, it becomes a primary alcohol. And that, again, should come as no surprise because we've talked about this before, and also we've mentioned, early on how you could take a primary alcohol and oxidize it all the way to a carboxylic acid, and an ester is just a derivative of a carboxylic acid. So this is just a couple examples, and the hydrogens on the or the hydrogens from the lithium aluminum hydride are nucleophiles, the hydride nucleophile, so they attack the carbonyl carbon. And in that case, what it forces is the alcohol part of the ester to eventually leave. Okay, and then that carbon that was in the carbonyl is what becomes the carbon that's now a primary alcohol. Okay, so this carbon that was a carbonyl has become just a CH2, and you get a primary alcohol. Now, the one sort of, curveball, I guess you could say, with that is if you have a lactone, then yes, you get a primary alcohol, but you also get a secondary alcohol. But really what that is it's like the alcohol byproduct. Okay, and we always followed up our discussion about reducing something with a hydride source, like lithium aluminum hydride, with an example or discussion, or both, of reduction with a Grignard reagent. And so we'll do the same with esters. So we can convert an ester into an alcohol with Grignard reagent. And the big thing here is recognize that it's going to become a tertiary alcohol where two of the substituents on the hydroxyl-bearing carbon are going to be the same. They're going to be identical because they come from the Grignard reagent. So esters react with two equivalents of Grignard reagent to yield a tertiary alcohol. And this just gives you the mechanism of that to show you the step-by-step way that it works. Okay, so typically you add the Grignard reagent first. Remember that the R group on the Grignard reagent, that just acts as a carbanion, and so it attacks the carbonyl carbon as a nucleophile, forms that bond. Okay, and so now if you think about leaving groups, because in order for this to happen again, something's going to have to leave. You can't add a fifth carbanion to this carbon. This carbon's already got 4 bonds, can't take any more than that. So something's got to leave. Well, relatively speaking, that's why this is labeled as a good leaving group. Relatively speaking, that's the best leaving group. Okay, so I don't know that I agree with the characterization of it as a good leaving group, but it's of the 4, that's the best one. So it leaves, the carbonyl is reformed, okay, and then that opens up for the possibility of another carbanion from another unit, from another equivalent of Grignard reagent to act as a nucleophile again. And so that's how you end up with 2 alkyl substituents. So you typically don't get the ketone intermediate. That's not seen. I suppose there might be some odd examples where that's possible, but generally speaking, it goes all the way. Whenever you introduce a Grignard reagent to an ester, it generally goes all the way to a tertiary alcohol, where 2 of the substituents on the tertiary alcohol come from the Grignard reagent. All right, so if you want to just check your work, and I'll talk through this briefly. So the biggest thing to recognize is, take your ester and you just kind of split it between the carbonyl and the oxygen in the ester function group. And one side is going to become, the side with the carbonyl, that carbonyl just transforms into a CH2 group because those hydrides from the lithium aluminum hydride are going to be nucleophiles on that carbon. Okay? And so that lithium aluminum hydride, that reducing agent, doesn't really bother the other side of the ester. But then in the second step, the addition of the acid is where you get the 2 hydrogens that make the actual alcohol functional group. So both of these hydrogens on these 2 alcohols come from that second step. Otherwise, if you don't do that second step, you'll have alkoxide ions. Or I guess in this case, that'll be a phenoxide anion. Okay, so now let's think about this question. So once again, I'll just kind of read the question and freeze the screen, let you think about it and come up with your answer there. So identify the Grignard reagent used in the transformation of an ester to become this alcohol. So this is the product, right? This is the product. So what's the Grignard reagent that produced this product? Okay, I did a little bit more than what the question asked, but just to help you see where the answer comes from, you can check your work here. So, the answer to the question is this. Okay, that's the Grignard reagent, but I thought if I show you the whole thing, you'll help make more sense. Why? So the two, you look for the two identical substituents. These are both ethyl groups, CH2, CH3, CH2, CH3, CH2, CH3. So these are the same. That's what tells you your Grignard reagent. Okay, so two equivalents of that, and both of those just acted as nucleophiles on this carbonyl to reduce it down to a tertiary alcohol. And so then the second step would be, that's where you just treat it with the acid. So this would be like your first step, and then the second step would be to treat it with some source of acid to get that hydrogen onto the alcohol group. Okay, so one more quick topic to go over. And that is, well, since we can make esters out of carboxylic acids and alcohol, what could we do with an organic compound that's got two carboxylic acid groups on it and a compound that likewise has two alcohol groups on it? Well, you can make some polymers with that, actually, because you can use those as monomer units that will come together and make a polymer. So polyesters, you've probably heard that term before. There's lots of different types of polyesters. It's a type of polymer. And so they are formed from dicarboxylic acids with diols, alcohols, right? Now the type of reaction, this is called a condensation polymerization, or it's a condensation reaction. And the reason why it's called that is because you condense two molecules together, okay, in a way. You split off a small molecule like water, it's usually water. It could also be like a HCl, some other small molecule splits off. But it's like you're taking substantial molecules and you're condensing them into one. So that's why it's called a condensation reaction. Okay, so for example, if you have this benzene ring, which is di-substituted, it's got a carboxylic acid group on each end, and you react that with ethylene glycol, which is ethylene or ethane, but with two alcohol groups, one on each carbon. And so they can come together and just build like a large molecule chain. And so, by the way, this is this polymer right here is PETE, polyethylene terephthalate, and that's a lot of times used in like soda bottles, soft drink bottles. It's used a lot for a lot of different purposes, but that's probably the most common one. Okay, so what if you don't have a di substitute? So if it's not two carboxylic acids and two alcohols, but you could still do this if the molecule itself has both a carboxylic acid and an alcohol in its structure, like these, like glycolic acid, like lactic acid. If you use those, you can make a polymer. Okay, and you can see that the reason why it works is because one end of the molecule can react with the other end of the molecule and just build a chain. So you could have polyglycolic acid or polylactic acid. The compounds with both a carboxylic acid and alcohol functional group can form polyesters as well. But the interesting thing about this is that polymers formed like this from molecules like this are biodegradable. Okay, so polyglycolic acid, polylactic acid, they're susceptible to hydrolysis later on. And so these are used for things like sutures. Okay, so the material that sutures are made out of, I don't know which one is preferred or anything like that, but that's what they're made of, because they will biodegrade.